All right, so tonight we're going to look at arc length and how we actually find the length of a line, basically. When we're looking at them, they're actually really simple to do if it's a straight line. However, when you have a curved line, it makes it a little more complicated to do. And it's even more complicated if it actually loops back on itself, which we're not going to actually look at right now for those. So, but we're going to look at tonight. So, all right. So here's the formulas for arc length. So you're going to want to write these down. So you'll notice there's two sets of them. Actually, move this over here. So we've got the first one is our set of high buggy. The first one is our set of when they're solved for y's and when they're solved in terms of x. And the second set of them is when they're solved in terms of y. So it just depends on the direction you're going to be going in. So, but notice the equations are the same. The first one is in Newton's format with the f prime of x, and the second set's in Leibniz's format with the dy over dx. So they're both the exact same. It just depends on how you like to write them. But they mean the same thing as the derivative of the function of x, or the derivative of the function of y in terms of this one. All these, when we're looking at an arc length, we're looking for an actual length. So all these are going to actually be definite integrals. They're going to be from A to B, or they're going to be from a starting point to an ending point. We are going to look at a situation a little bit later in this class where we're going to an indeterminate amount point, which is basically known as the arc length function. And we'll have one of them be an x value that we're going to look for. So, but it's the same concept. We're just going to plug those in. So all these are going to be definite intervals. There won't be any c's or anything else in these. All right, we got this down. All right, so let's look at an example. So we're going to look for the length of the arc of a semi-cubical parabola. So it's y squared equals x to the third, and we're looking at it between points 1, 1 and 4, 8. So the first thing we're going to have to do for any of these problems is we have to solve it in terms of one of them. So either the x or the y. So let's take this one and we'll solve it in terms of the y. And of course, my tablet decides to be funky. There we go. So we've got y squared equals x to the third. All right, so this one's simple. We're just going to take the square root of both sides. So y ends up equaling x to the 3/2 power. All right, so now remember the formula is from A to B of the square root of 1 plus the derivative of x squared. All right, so let's plug our information in. So we're going from 1 to 4. Since we're solved this for in terms of x, we're going to use the x values. So we have 1 plus, oh, and I need the derivative of that. So f of x is x to the 3 over 2. F prime of x is 3 over 2 x to the 1/2. So I've got 3 over 2 x to the 1/2 squared dx. Any questions with those? So the one thing when they're looking at the arc length is the integrations are going to be a little more complicated than what we saw in chapter 6, because you've got all the stuff in chapter 7 now. So simplify this down. So I've got 9/4 x dx. So which method do you want to use to solve this?
The arctan one, correct, or am I?
So with arctan, it's the a plus or the a squared plus x squared when we're looking at those, like the trig substitutions and stuff.
So there's yeah.
Huh?
That makes sense.
We're going to use U substitution.
Yeah. Remember, the first thing, once you've simplified it down as much as you can, look at U substitution. All right. If you can't use U substitution, let's go on to some of the other stuff. Well, let's look at the U substitution first. So in this problem, if I make U 1 plus 9/4 x, du is just 9/4 dx. And then if I want, which will make my life a little bit easier so I don't have to substitute back in the 1 plus 9/4 x, I actually can plug in and find those other two. So when x is 1, u is 13/4. And when x is 4, u is 10.
Professor, could you say that last part again, please?
Yeah, so basically, remember when we're doing the definite intervals, we can change the actual starting point and the ending point based on u instead of the x. This allows us not to have to go back and substitute back in. We can actually solve it in terms of u and just plug those values in. It saves me that one extra step at the end.
Sorry, I don't think I understand in this case.
Okay, hold on. Let me actually, I'll show you in a second. I'm rewriting one thing and then you can see how it actually shows up and then maybe a little better. All right. So we've got this. So I'm going to go through and I'm going to change. So basically all I did to get these is I plugged the 1 into x and the 4 into x to figure out what u is at when x is 1 and x is 4. Because I'm going to replace those values too. So this new problem that I have becomes 13/4 to 10. And it's the square root of u du. Oh, and I got to do one thing. I forgot to move the 4/9 over, and the 4/9 is in front because I bring that over to that side. Save the problem. So basically all we're doing is we're taking all of it and changing it all to u's. And now I want my problem solved in terms of u's instead of in terms of x's. It doesn't actually, you can ignore this step over here if you want. You just have to substitute back in the u at the end, back with the 1 plus 9/4 x. And you're gonna do the exact same thing anyway, by plugging in the 1 and the 4. Does that make sense or no?
Okay, so all we're doing is just switching it over to use.
Yeah, basically, just to make my life easier. Kind of remember when we did the trig substitution problems, when we had it, if we changed them as we went, when we were doing the definite integrals, I didn't have to do the triangle method and everything else at the end to go all the way back to the x's. It's kind of like that. It just makes your life a little bit easier. In this problem, it's not that big of a deal, but it's a good habit to get into, especially in the more complex problems. So now we got to do our integration. So we have the 4 nines up front. And the integral of u to the 1/2 is 2/3 u to the 3/2. And we're evaluating that from 13/4 to 10. So I've got 8/27. And if I plug in 10, I've got the 10 to the 3/2 minus 13/4 to the 3/2. And I would actually leave it like that. The book simplifies it down a little bit more, but you can leave it just like that. So the only difference by doing the u's is if I change that back to the 1 plus 9/4 x, I'd have plugged in 1 and 4, and it would have given me the exact same answers there. It wouldn't have actually changed anything. So that would be the arc length of that arc. That'd be how long that arc is right there.
And the mindset there was to use u substitution to avoid using
Oh.
the arctan.
No, because our arctan,
Or sorry,
So-
the tan.
and this one, you wouldn't have wanted to use the arctan because we don't have, it's not in the right format. This one you want to do u substitution for. The arctangent is when you have a situation where you can't do the u substitution.
Which is specifically
So hold on, let me get the. Because I know which one you're trying to use.
I'm trying to see that either fit the a squared plus x squared version, right? And I guess that's really the only one that would make sense because the other one was 1 over x squared plus a squared.
Oh, no, this one. I was looking at the wrong section. Yeah, it's the x squared plus a squared.
So the square root of a squared plus a squared, right?
No, so okay, so hold on, there's two different things. So this is the arctan rule. This is the arctangent rule. That's the one that gives you arctangent.
Right, that's not the right format for this one.
Right. And then there's the,
Trig sub.
right. Now the trig substitution one, you need, and it's still in terms of a squared and an x squared. In this problem, we don't have x squared anymore. In this problem, we have 1 plus 9 fourths x. There's no square.
Oh, so the degree isn't big enough?
Right. So we need the square to do this. And the reason that we need to do this for the square is because if I did use substitution, I'd be left with the 2x. And if I don't have an x left over outside to get rid of it, I'm kind of screwed. And this problem that we just did, we don't need to worry about that because when I do the use substitution, there's no x left because I didn't have x squared.
Got it.
Okay. The nice thing is the next one we're going to do has that. So you will see the difference between the two. So let's look at this one. Now this one's already solved in terms of x. So we're going to use the other format. So we're going to use this one. We're going to do it in terms of y. So I've got x equals y squared. So f prime of x of y equals 2y. So my integral, I'm doing this one from 0 to 1. And now remember, when I'm doing these, I'd want to use the y values for it. And this problem, the way they picked it, it doesn't make a difference. But since it's in y's, I'd use the y's and not the x's. So I have 1 plus 4y squared dy. Now, if I had tried to use u substitution on this one to make that the 4y squared, the du is going to be 8y dy. Notice now I have the y left, and I don't have an extra y in the problem. So now this one I do have to do the trig substitution for. Does that make sense? So for this one, to do my trig substitution, I'm going to make y 1/2 tangent theta. So my dy is 1/2 secant squared theta d theta. And then this part in here, so my square root of 1 plus 4 times 1/2 tangent theta squared ends up equaling just 1 plus tangent squared theta, which is secant theta, secant squared theta. So this whole part equals just secant theta.
Professor, could you go over how to, I mean, I know that probably comes naturally to you, like choosing y equals 1/2 tan theta, but is there a systematic approach to get the right version of
Yeah,
it?
we're using this part right here. We're using this one for it. Okay.
Right, so we know it needs to be in that format.
Right. So that's the format I'm using. So my goal, so right now inside my square root, I have 1 plus 4, sorry, y squared, right?
Mm-hmm.
I need to get it to be 1 plus tangent squared theta. That's what I need to get it to.
Mm-hmm.
So the question is what do I need to make y to make that happen? Well, I need to get rid of the 4. So right now, this part right here is 2y squared. So tangent squared theta has to be equal to 2y squared, right?
Right.
Correct?
Mm-hmm.
So that means 2y has to equal tangent theta. So y equals 1/2 tangent theta. So it goes back to the goals. What's the goal? The goal is to get that to be 1 plus tangent squared theta. So I can do my identity rule. So then you can solve through it and figure out what's the piece that I need left for that. And the only difference is if there's a number, like in this case, there was already a 1 there, so I didn't have to worry about it. Remember, if there was like a 4 or something like that, I need to factor that out before I do the actual part. So that would actually change. That's where that A comes from in front, is because that's going to be the piece that we're going to factor out. At this point, the A wasn't 1/2. That 1/2 is there basically to get rid of the 4 that I had in the problem originally.
Got it. That makes a lot of sense. Thank you.
No problem. Move this over here. All right, so we're here. So the other things that I'm going to want to do is, again, we're not going to want to have to go all the way back. So I want to change my 0 and my 1 into thetas. So I don't have to go back to the y's. So if y equals 0, I have what value is going to make that would be, so I have 0 equals 1/2 tangent theta. So 0 equals theta. And then if I have 1, I have 1 equals 1/2 tangent theta. So 1/2, or actually not 1/2, 2. So 2 equals tangent theta. And there is no simple way for, there is no simple one of that one. And I run out of. I'm going to rewrite this because I ran out of. So y equals 1. I have 1 equals 1/2 tangent theta.
So is that just going to end up being arc 2?
Yeah. So then I'm going to have the arctangent of 2 equals theta. which, so I don't have to worry about this. I'm going to set that to A. I'm just going to pick a letter. This way, the only reason it means actually nothing. You can write the arctangent of 2. It's just going to save me work when I'm writing out the integral going through it, but you don't have to do it. You can actually just use the actual number if you wanted to. All right, so my original problem, so we had 0 to 1, 1 plus 4y squared dy. So I've got the square root is secant theta. So we have 0 to a. And that's just so I don't have to write the arctangent of 2 up there. That's what I was saying. So this whole part becomes just secant theta. And then my dy was 1/2 secant squared theta. C theta. So I'm going to pull out the 1/2, and I'll just write up here A equals arctangent of 2. So we have that there. So I have secant to the 3rd theta, C theta. All right. Okay, so how do we want to integrate this? So we have secant to the 3rd theta. We've actually done this problem. So I can't necessarily do the trig integrals because I don't have a tangent. I can't do the trig substitution we've already done, so we're not going to use that. So I'm not going to do, so the only other way that we have to do this is integration by parts. So if I make u, so what I'm basically going to do is I'm going to split this. So I'm going to split this up. And now your next question is, how on earth do you know how to do this? It's called, again, you're stuck. So what do we have? What's my options that I have to do? So I can't do the trig integrals because I don't have a tangent. So let's figure out some way to get a tangent. So if I make it this way, this is going to become tangent theta. And this will become secant theta tangent theta. So now I have some tangents.
So is the du there secant theta, tangent theta, d theta?
Yeah, I just didn't have room to write it, so. All right, so I now have 1/2 0 to a Oh, actually, sorry. Integration by parts. So I have the secant theta tangent theta minus secant theta tangent squared theta d theta. Remember, again, we're basically going along the integration by parts process now. So that's the thing with a lot of these. It's you just have to start looking at the different processes to figure out, all right, where am I? What do I have? What do I need to continue to go forward? Because we have to be able to do the integral of this. They're not going to, obviously, at this situation, they're not going to give you something you can't integrate. So we did the trig substitution to get rid of the square root. And then we had to do use of, or the integration by parts to be able to break up that secant to the third. So we're here now.
It's one of those where we have to do it like the sine and do it one more time and then divide by 2.
What do you mean? What did you say? I missed what you said, sorry.
So this is one of those where eventually the left is, we're gonna get the left's value on the right and then divide by 2.
Yeah, basically. So the next step we're going to do is we're going to clean up this over here a little bit. So we have secant theta, tangent theta, and this is going to become we have secant theta, and then that's 1 minus secant squared theta. Oh, sorry, I have that backwards. I'm used to using the other one. Secant squared theta minus 1. There. So, still extra. So we have secant theta tangent theta minus the integral of secant to the third theta minus the integral of secant theta. I have d thetas in there. I swear to God, I just didn't write them.
And the reason why we're putting it in terms of secant theta as opposed to just where, you know, it was with just sines and cosines, we just did it again. Is there, be able to speak to that, Professor?
Because if I turn them into sines and cosines, I would have sine to the third over, well, sines for secant would be 1 over cosine to the third power.
No, I'm not talking about turning it into cosines and sines. Before we would just do it again, integration by parts again, trying to get. Oh, I see. So we're trying to get it obviously in terms of secant third theta.
Yeah, this one ends up being that loop thing.
Right.
So we're gonna end up with the secant to the third again in there. So that's where that piece comes out. So if I bring this over, so I have 1/2 secant theta, tangent theta. This piece, when I bring it over, will duplicate this. So on this side, I end up just with secant to the third theta d theta. And then I have minus 1/2 of the integral of secant theta d theta. Oh, I lost the theta in here with everything all these. I lost the 1/2 in here somewhere. Oh, I know why. Okay. So when you're doing, because the halves on both sides, don't worry about the half until the very end. I distributed it, should be fine. Oh, I'm gonna put it there. That's where I'm gonna put it. Okay, never mind. All right, so we now have to do this one. Now this is the one where we had, there is just an integral that you have to remember for it. So I have 1/2 secant theta tangent theta minus 1/2. And this one was ln of secant theta plus tangent theta. Trying to figure out, I lost the 1/2 in here somewhere, and I'm trying to figure out where I lost it.
So yeah, so there was a 1/2 on the left side of the equation originally, right? Which we
Yeah.
have. So do we want to put that there, or did you account for it already? On the
That's what I'm trying to figure out, because I'm like, I've lost, because it's supposed to be 1/4. The final answer has a 1/4 in it. And I'm trying to figure out where I lost the 1/2. Because if you didn't have that 1/2 there, I would divide it by 2, which would have given me the extra 1/2. But I thought,
What about the integral to secant cubed?
because I distributed that 1/2 to each one. Oh, sorry, that there. So if I distribute the integral, that gives me negative 1/2 secant to the third. Which was what gave me the 1 over there. Honestly, I have to redo it and figure out where I missed the 1/2. But it ends up actually supposed to be 1/4. Because that one gives you 1/2 to begin with. And there was already a half there, but I thought I dealt with it when I did the problem, and I can't figure out where it is. I think what I was supposed to do is just ignore that part and just do the secant to the third part, but I can't figure out why I'm losing the half in the problem. That's where I'm stuck. I'm not going to go through and redo the whole entire problem right now. I will before I post the notes though. So if you want to stick around at the end of class, I will go through this problem again. So I have the half right.
I'm confused where those secant theta plus tan theta comes from, Professor.
Okay, that I can tell you. Give me 1 second. Let me just finish writing this back out. That's integration by parts. That's right here. So we did the u du v dv. So remember the integration by parts, the rule is uv minus the integral of v du. So that's where the secant and the tangent came from out front.
Oh, so now we're just doing all of that in one step.
Well, I didn't. So here's that was the u substitution piece that I did right there, or the integration by parts part. So I did that integral right here. Because that was my u, that was my dv. Those things, and I plugged it right back into the problem.
Uh-huh.
So that's the u, that's the v. That's the, well, the only thing I did was I put the two tangents together. So it's secant tangent d theta. But
No, I know, I get that. I'm talking about the last step you did in
On this
all of this. No, on the next page.
yeah, so that was my integration by parts problem.
Yeah, but then there's just the last minus secant theta on the third line. Obviously that you distribute the 1/2, I get that. And then there's 1/2 ln of secant theta plus tan theta. Where does the secant theta plus tan theta come from?
Oh, because that's the integral of, that's that. The secant theta plus tangent theta, that's the integral for secant theta. That's just a rule.
Plus, though, I got the.
Yeah.
Oh god, I guess I don't have that identity. That's just an identity?
Yeah, that's just one, yeah. That's one I gave you back when we did section 7.2. It's right here. That. All right. Let's finish this one. Okay. So we started with the one thing I have right now is I have arctangent of 2 is A. So that's the only other thing I have. So we've got to plug in 0 and A. Okay. So if I do plug in, I have the 1/4 out in front. We have secant of A times tangent of A minus ln of secant of A plus tangent of A. And zero, secant of 0 is 0 and tangent of 0 is 0. So those are all gone. So I need to figure out what tangent of A is and secant of A is. So this right here is easily just becomes tangent of A is 2. That makes sense? So now I got to figure out what secant of A is. So I know that secant squared of A is 1 plus tangent squared of A. So that means secant squared of A would be 5. So secant of A is square root of 5.
Wait, what? Oh, okay, that makes sense.
Because remember, tangent of A is 2, so tangent squared of A is 4. So this is 2 square root of 5 minus ln of positive square root of 5 plus 2. So the reason why, if you remember at the very beginning, I said we weren't going to plug in, I didn't want to use the arctangent of 2, is because instead of putting A's, all these would have been arctangents of 2, which would have made it a lot harder to see what we were actually going to be doing in the problem. So sometimes by just replacing it with a letter, it makes it a little bit easier to figure out what you're going to be doing with the problem. Like the tangent part would have come out to be nice because tangent would have been arctangent, so that just would have been 2. But it would have been really hard for you to see what secant of arctangent of 2 would have been. So you still would have ended up doing something like this to figure out what your secant was. Makes sense or no? A lot of the stuff in this chapter, 8.1, 8.2, 8.3 that we're going to do, honestly, this is one of those ones where, remember I was saying before the algebra is what's going to mess you up? This is getting to the point where it's the trig stuff that's going to mess you up. It's not the new rule. The new rule is easy. This, I think you all could do. That's not the hard part. Okay. The hard part is remembering which rules we're doing in this problem. So like this was my original problem that I started off with. It's like we had to do trig substitution to it. And then we had to do a integration by parts to it. And then we had to actually go through and use all the trig rules to simplify the problem down. So it really comes down to what rules are you going to use? And it's a lot of those from chapter 7. Which for the most part, the people who did the ones I graded actually did really well in the test. So. Now we'll see how well you actually put them all together. All right, one more problem to do, and then I'm going to go back and fix that one and figure out where I lost my 1/2. All right, so this one's looking at what's known as the arc length function. If you notice, it's exactly the same equation. This function right here is almost identical to what we did before. The only difference is this one little thing up top there, that little x. What this is going to allow us to do is it's going to allow us to come up with an equation that'll allow us to find the arc length of any of those functions given the starting point. All right, so you still need a starting point. So we can't take the arc length function and do it as a completely indefinite interval. We have to have a starting point for it, and then we can have it go on forever to after that point, and then take it, figure out where we want it to end afterwards, basically. But you always have to have at least a starting point. Or I guess technically you could also have an end point, but I don't see why that would, most people would do it that way. So we're going to do the same thing. I got my equation. So the y equals x squared minus 1/8 ln of x. So I need to find my f prime of x. So we're taking the derivative of this. So the derivative of this is 2x minus 1/8x. So now my integral,
You have derivative of y?
what was that?
You have y equals x squared minus 1/8 ln x. Wouldn't it be f derivative of y?
No, the f derivative, it's, remember, y is f of x.
Okay, sorry.
That's okay. Yeah, y and f of x are the same thing. So, but yeah, this, remember, this is just basically telling you which values it's solved for, or it's in terms of. All right, so now we've got my integral from 1 to x. And we have 1 plus 2x minus 1/8x squared dx. All right. What do you want to try?
Are we gonna have to do partial fractions?
Partial fractions is when we have a rational function or rational equation. So I have something over something. So we're not going to do partial fractions with this one. So really my only options when I have square roots like this is either I do something with the actual square root to make it simpler and break it down. Or if we have the squares, we can do trig substitution to it. So since this one really has a whole bunch of algebra in it to begin with, let's see if we can simplify this problem down.
Oh, right, because we just had 2 x's on the inside that can be easily put into 1x. Like, what is that? 15x. 15/8x, right? We just do
Would it
that.
all be squared?
Yeah, it
Exactly.
would still be squared.
Isn't that simpler?
Yeah.
And then we could just use tan,
Wait, no, that
think
won't be, actually, wait, hold on. You can't do that. This is,
Oh,
this
that's
is
right,
one of those
'cause it's
situations
square.
where it's like, I'm like, yeah, that sounds right. Wait, that won't work. I'll show you why. All right, let's see.
right, because of,
The X is not on top.
oh,
That's this.
God. Right, right.
Remember, it was ln of X, which becomes the 1 over X. So yes, the X is not on top, so we can't do that. So, but let's look at what we got. So we got 1 plus this, right? Let's FOIL this out. So I've got 1 plus 2x times 2x would be 4x squared. I have 2x times negative, that one would be, what is it, negative 1/4. And then I have another negative 1/4. And then I have a plus 1 over 64x squared. So I've got, if I break all this down, I've got 4x squared plus 1/2 plus 1 over 64x squared.
You mean minus 1/2?
Nope. You got the 1 in front. So you have 1 minus 1/4 minus
Oh,
1/4.
oh, Right.
So when you have something that looks like this, and we got to factor it, if we look at the first and the last terms are both perfect squares. So I've got 2x and 1 over 8x, right? So we try that and see if that would actually give me my middle term correctly. So in this case, I have the 4x squared. I'd have plus 1/4 plus 1/4 plus the 1 over 64x squared. So that does work. And the crazy thing about it is I just taught that to my Algebra 2 class last week. So you look at the first and last terms, if they're perfect squares, you can break them down basically the square root of each one of them and then plug them into this format. And then the key is the middle still has to work. So the easiest way to do it is to actually try it and see if the middle ends up working. If not, then that process didn't work. We have to try something else. Now remember, the entire, go ahead.
Continue to simplify that and then take and get 16x squared plus 1 over 8x.
Wait, which one? Hold on. Where are you getting the 16x squared from?
No, I'm an idiot. I'm trying to square what we just
Oh,
made up all nice.
gotcha. So here's the nice thing about this whole thing. We took this whole thing, right? This part is my square root. So I have the square root of 2x plus 1 over, what do we write this? 8x squared. So this whole thing becomes 2x plus 1 over 8x. No more square root. All right. So. Okay, so we good to there? So now we have this. You'll notice one little thing. First of all, I hate writing T's. So if I can avoid writing T's, I'm going to avoid writing T's at all costs. But I can't use X because if I use an X, it's going to be really screwy when I try to plug in an X. So if you like to use T's, which they did up here, use T's. If not, pick something else. It can be any letter you want. So now we're just going to do the integral of that. So this ends up becoming, we've got a squared plus 1/8 ln of a. And we're evaluating this whole thing from 1 to t, or from 1 to x. So my final answer ends up being x squared plus 1/8 ln of x minus 1. So now I can take any point on this function that I want and plug it in and find the arc length. But notice that there's still not a C. And that's the piece that was really important. That's why we have that starting point. If we didn't have the starting point, you'd have a C and it wouldn't work to be able to solve the problems. Okay. All right. Any questions with that? So 2 takeaways from tonight's lesson. First one is that's your arc length formula. All you really need to do your arc length formula. Second takeaway, you have to remember all the different ways to iterate from chapter 7. Because that seems to be the biggest struggle that people have. It's like, how do you decide what to do? And that's really where that section 7.5 comes into play. It's like, you just got to keep breaking it down to figure out, it's like, okay, if I'm stuck, where do I go next? So other than that, really all you have to do with these. And then if you're looking for the function, it's just the starting point to the x value. All right. Other than that, this is it for tonight. So I would highly suggest picking some of the problems in chapter section 8.1 and working on them. If you get stuck, like I said, send me an email. I can send you the solution guide to it so you can see how they are broken out and done. a lot of this is going to be figuring out where to, like I said, break down your problems. What process to use, when to use it. You don't want to jump right to the complicated things if you can simplify things down first. And partial fractions and trig substitution are the harder things. So you don't want to do those first if you don't have to. And this was a perfect example of where simplifying down the problem first actually makes your life a lot easier. This.